So next up, Yifeng Teng will be telling us why competitive markets converge to first price auctions. So take it away.
Okay.
Yifeng, oh great, thanks.
Hello everyone. I'm Yifeng Teng from University of Wisconsin, and today I'm going to talk about the paper "Why Do Competitive Markets Converge to First Price Auctions?" And this is joint work with Renato and Balu from Google Research New York. Okay, so the problem we study arises from the online display ads market, where the website may have multiple ad slots to sell to the advertisers to display their ads, and the advertisers would compete for the ad slots. So one important way these days for the sellers to sell their ad slots is through the ad exchanges. And the ad exchanges serve as the platform for the publishers to sell their inventories, and the advertisers will purchase ad slots via the real-time online auctions. So fix a particular ad slot sold by the publisher. The structure of the market looks like what's shown here. And the publisher will sell the inventory resource through multiple ad exchanges. And the advertisers at the same time will go to different ad exchanges to bid for the ad slots in the web page. And usually for the different exchanges, they will face the same set of advertisers. So if we isolate a particular ad exchange, the ad slot is sold through the real-time auction, and it is a single item auction. And what kind of auctions are used by exchanges in the real world? So several years ago, the markets were mostly using the second price auction with reserve. And in such an auction, each bidder will submit a bid simultaneously, and the bidder with the highest bid that exceeds the reserve wins and pays the higher of the reserve and the second highest bid. So why does market trust use second price auction? And one important reason is that everyone bidding truthfully is actually a dominant strategy equilibrium in an auction. And the second price auction itself is actually the unique optimal static auction that satisfies this property. So in such an auction where everyone's preference is to bid truthfully, it would be easiest for bidders to propose their bids. And however, the trend in recent years shows that the exchanges in the markets are switching to first price auction with reserves. So in the first price auction, each bidder will just submit a bid, and the bidder with highest bid that exceeds the reserve wins and pays her bid. So why do the exchanges in the market switch to first price auction? So one significant reason that has been mentioned the most in the media is about the transparency. So the second price auction itself is not credible, which means that the auctioneer can deviate from the rules he claimed before the auction. For example, there are two bidders in a second price auction. Each was bid 5 and 10 respectively. And then the seller can manipulate the auction as follows. The exchange reaches to the second bidder saying that, okay, congratulations, you bid 10, you are the highest bidder. And I tell you that the second highest bid is 9.9, so please pay that price. And by this way, the seller can easily increase his revenue by implementing the different auction. And the bidders will not recognize it because from the bidder's view, the seller's action is actually indifferent to them, whether they are doing it correctly or not. So there was some survey saying that such exact process that the exchange claims that they are running second price auction, but sells the item through the first price auction is actually done by a lot of the exchanges. So on the other hand, first price auction doesn't have this issue. Because for a winner, the reserve and the highest bid are both known to the bidder. So the seller cannot really manipulate the allocation and the prices. And the first price auction is actually the unique static and open auction with such property. And also in the first price auction, the allocation and payment rules are easy to understand, and this will reduce the complexity of the entire process. So although the transparency and complexity are two most important reasons mentioned by the product directors from multiple companies in the media, we know that the exchange companies will never change if it really incurs some huge revenue loss. So the question we want to ask is that what do auction theory and game theory say about moving to the first price auctions? And in this paper, we propose a game theoretical analysis of the market, justifying that the market converging to first price auction is actually a rational result. Okay, so now I will introduce the model. So suppose that we have a single publisher that wants to sell one ad slot and reaches to M exchanges. And each exchange will control a lambda j fraction of the publisher's traffic. And there are n bidders, and each with value drawn independently from some known distribution that are publicly known to the exchanges and the other bidders. And each bidder has quasi-linear utility. So in the first stage of the game, each exchange J is asked to propose an auction. So different exchanges may propose different auction. For example, the first price auction with no reserve, the second price auction with reserve 10, and so on. And in the second stage, each bidder will be asked to submit a bid that is determined by her private value to all of the exchanges, while the bidding function is determined by other bidders' distribution. So the key assumption in this model is that we assume that each bidder will submit the same bids to all of the exchanges. So this is a strong assumption that doesn't hold for all bidders who customize their bidding strategy for different exchanges, but actually advertisers from a significant fraction of traffic are agnostic to the specific auction used in query. So why is that true? We may observe that the bidders always track their key performance indicators like the impressions they won and do not have exchange-specific goals. And advertisers may often participate in preliminary auctions that are not exchange-specific within ad networks. And developing exchange-specific bidding strategy can be costly, especially when many exchanges are using very close auction formats. So another assumptions that we use in this work is that we assume bidders have ID values, that the values of each bidder is drawn from the same distribution. So we actually observed that the main result is already technically involved even for the ID setting. And for the non-ID setting, even the equilibrium for the first price auction is hard to reason about. Okay, so we've seen assumptions. Let's get back to the game. In the second stage, we assume that each bidder will respond to the average mechanism proposed by the exchanges. And we also assume that the bidder's bidding strategy will form the Bayesian-Nash equilibrium. And in the ID setting, we assume that the bidders have symmetric equilibrium. So then get back to the first stage. Knowing that the bidders in the second stage will behave rationally, each exchange will want to propose a mechanism to maximize its own revenue. So this is the objective of the players, which are the exchanges, and the class of options that can be proposed by the exchanges are the action space. And the main question we want to ask in this model is that what is the equilibrium of exchanges in the two-stage game? Okay, so now let me show our main results. The first theorem says that suppose that we only allow each exchange to propose a high-bid auction. What do we mean by high-bid auction? It should have three properties. The first property is that the highest bidder should always get the item. And the second property is that the winner always pays no more than her bid. And the third property is that the rest of losers all pay zero. So in this market, every exchange proposing the first price auction is the unique equilibrium of the game. So we also show that all three properties are necessary, and removing any one of them will lead to the equilibrium not be on the first price auction market. So we may observe that the second property and third properties are really natural in the market, and they are reasonable assumptions. But the first assumption is actually not that reasonable, because most auctions used in the market, like the auctions with reserve prices, does not satisfy this property. So condition on the highest bidder has bid smaller than the reserve, the highest bidder will lose in the auction and does not get allocated item. So what happens in the market with reserve prices? So for the auction with reserve prices, we can still manage to analyze a large class of mechanisms. In particular, we assume that each exchange is only allowed to propose a first price auction with reserve or second price auction with reserve. So this still characterizes most of cases in this market. So our theorem is that in the equilibrium of the game, every exchange must propose first price auction with reserve, and no one will run second price auction. So these two theorems provides an alternative explanation of why the competitive market is actually converts to first price auctions. And we will now try to explain the proof of the first theorem. So it says that in the high-bid auction market, every exchange proposing first price auction is the unique equilibrium. So the difficulty of the problem comes from the following fact, that each bidder will bid optimally against the average mechanism she observes. So this means that suppose that the exchange will want to deviate from its proposed auction, the average auction of all exchanges will change. And then the equilibrium bidding function of all bidders will also change, which makes the analysis hard. So how to solve this problem? We may observe the revenue equivalence theorem, saying that any two auctions with the same allocation rule for the same value bidders will have the same revenue. So one particular example for the high-bid auction market is that suppose that we have NID buyers, and we may see the first price auction and second price auction have the same revenue. This is because that in the first price auction and second price auction, the bidder with the highest value will have the highest bid, and they will get the same allocation. Then we can apply the revenue equivalence theorem, and this can be applied to every single high-bid auction. And in particular, the following high-bid auction, that is the weighted average of the mechanism proposed by the exchanges. So we can view the weighted average revenue of all of the auctions as a constant, no matter what auctions are proposed by the exchanges. So we may observe that by the definition of the high-bid auctions, losers always pay zero, and the winner does not pay more than her bid. So this means that if we fix the bids of the bidders, the first price auction actually collects the highest payment among all high-bid auctions. This means that an exchange using first price auction will always get at least average revenue. And the equality holds only when every exchange is proposing first price auction. So for the pie representing the constant revenue of the average auction, we may see that if the revenue of exchange 1 is below average, it can always try to switch to a first price auction to gain a larger fraction of the pie. So this means that in equilibrium, all exchanges will try to propose the first price auction, and this proves theorem 1. So for the market with reserve prices, everything will be completely different. And we will just see some observations in the market. So the first observation is that we cannot directly apply revenue equivalence theorem. So even when the vector of reserves of all exchanges are fixed, the pie we showed last page is completely different when the exchanges change their proposed auctions. So consider the following two cases. In the first case, both exchanges propose first price auction, each with reserve R1 and R2 respectively. And in the second case, the two exchanges are proposing second price auction. So suppose that R1 is smaller than R2, then we know that in the second price market, bidding truthfully is the equilibrium. However, in the first price market, everyone will try to shade their bid. In particular, conditioned on the case where the winner has value R2, the winner will try to shake her bid in the first price market, so she will only win the first auction, that is first price auction with reserve R1, and lose in the second auction because she doesn't meet the reserve. However, in the second price market, she will bid truthfully, so this means that she will win in both auctions. This means that conditioned on the bidder having this bid, the allocation in both auctions are different. This means that we cannot directly apply revenue equivalence theorem. So actually in the paper, we kind of brute force analyze the bidding equilibrium using the first order conditions, and I will refer you to the paper to see more details. Okay, so the second observation in the market is that the bidding function of the bidders may not be continuous. This also makes the analysis harder. So why is that? So consider a case with two bidders, each with value drawn uniformly between 0 and 1. And there are two exchanges with equal traffic, each propose first price auction with reserve 0.3 and 0.5. So we may see that for a bidder with value around 0.6, the bidder will be indifferent between the 2 points, the lower bid A and the higher bid B. So if the bidder bids around A, she will win only in the first price auction with reserve 0.3, but her payment will be lower. If she bids around B, she will win in both auctions, but she will pay higher. And bidders with higher value will bid above B, and bidders with lower value will bid below A. So this is where the discontinuity comes from. And the last observation we want to make is that in the market, every exchange proposing first price auction with the same reserve is never in equilibrium. So there are two implications of this observation. The first implication is that every exchange proposing first price auction with reserve 0 is not in equilibrium. So this justifies that in the first theorem, we always need the winner to always get allocated. Otherwise, first price auction is not an equilibrium. And the second implication is that every exchange proposing first price auction with Myerson's reserve is not in equilibrium. This means that the existence of computation between the exchanges really lowers the total revenue of the market. And forcing every exchange to use the same reserve may benefit the exchanges and the publishers. Okay, so now I would like to conclude my talk. We propose a game theoretic model for the competition between exchanges in the X market. And we show that the first price auctions are the reasonable choice of the environment because they are usually the equilibriums. And for the future questions on the model, we may ask, what will the equilibrium be for the broader class of auctions? And can we generalize the result to some kind of non-ID setting?